So when we're given a graph, right, given a picture of a function, given a graph of a function, -2, -1, three, 4, 1. So that is what we have, right? A graph of a function. I find what is f of 1, what is the limit of f of x when x approaches to 1, what is f of 4, and what is the limit of f of x when x approaches to 4. Right, so that thing was what we're looking for. Right, so first of all, the function, right? The function is defined at 1 at y equals 2. Right, so we have f of x is defined when x equals 1, the y value is 2. So f of 1 is 2. Right, but the limit of f of x approaches to the left is 4, approaches from the right is 1. They don't meet at the same point. Approaches from the left to 1 is 4, approaches to 1 from the right is a different value. So this limit does not exist, right, since they don't meet at the same value. At this one, f of 4, at x equals 4, that's a hole along the path. Let's dig it out, but doesn't define anywhere else. We will say f of 4 is undefined. Oh, we say the function is not defined at 4. In other words, it's undefined. F of 4 is undefined. Then the limit we can see along the path approaches to left, approaches to right, approaches from left to 4, approaches from right to 4. The y value is 2. So the limit when x approaches to 4 of the function is 2 here. So for some other graph, Right, certain function at here, and negative 2, 2 is a whole digging out, and for the y-axis we have vertical asymptote along the path from left and right, and the point 3 is here. After that, right, from the bottom it's going up to 1, and then we have a straight line from 2 down to negative 2, and then that's the 2, right, and then goes up. Right, that's certain things. So find what is f of negative 2, what is the limit of f of x as x approaches to negative 2, what is f of 0, what is limit of f of x when x approaches to 0, what is f of 1, what is the limit, and what is f of 2, and what is the limit. I'm asking for 4 things. The function and its limit. At negative 2, at 0, at 1, and at 2. Right, so first of all, at negative 2, well, the function we're looking for the solid dot, right, the solid point, which on the vertical line of negative 2, we don't see any solid point, which means this is undefined. Right, for the limit, we will move along the path and to see where they meet. Right, they both from the left and from right meet at y equals 2, so the limit is 2. Right, for 0, they both goes down, and from bottom to top, from top to bottom, which is the vertical asymptote. Right, so this one is also undefined. But no. The f of 0 is actually, sorry for my mistake, right? It is the solid point we're looking for, that the value is 3, but the limit is going along the path. That one is vertical asymptote, so this one not exist, the limit. Right? The limit doesn't exist. F of 1 will go to the solid point, that the point is defined at 2. But the limit of 1 approaches to it from the right or from the left. From the right it approaches to the value 2, from left it approaches to the value 0, which it doesn't exist. Right, the last one, f of 2, is defined at negative 2. And the path is also matches at negative 2, so the limit and the function value agrees to each other, that we get at x equal 2, have both the limit and the function values. Right, so for the function, we're looking for the solid point. For the limit, we're looking along the path of the function, along the path from left and from right. Right, the given function that's a straight line all the way up to -2, and at -2 we have an open circle. Right, then go down to -1 for x to be -1, then horizontal line approaches to -1 all the way to x equals 0. Right, then that here is an open circle. At 1 is defined at 1, and after 1 is the horizontal line of 2. Right. And at -2 we don't have anything being defined, so f of -2 is undefined, but the limit exists approaches to the y value of 0. F of 0 here is defined at the solid point of 1 here, but the limit at the left it approaches to -1, at right it approaches to 2, that it does not exist. Alright, so that's our first section to define to find the limit numerically, which is draw the table to find the limit, or find the limit graphically, which is on the graph, right, to see what the limit approach is. And be careful or be clearly distinguished between the find the function value or find the limit, right? That's two different technology. So that is our first section, and then section 2.3. Evaluate the limits. Evaluate limits analytically, which means algebraically do some simplification if we could able to do, and try to substitute it. Alright, so before we move on, right, that's basic limits. Let B and C are constants and B an integer. A couple of basic limits is the limit of x approaches to a certain value c of a constant b is just the b. The limit of x approaches to c for a x, or just directly substitute into the x, that will give us a c. Right? And the third one is for x to the nth power, the limit when x approaches to c will be c to the n, which basically, right, these are constants, are linear function. This one is nth power exponent of x, right? They are continuous function. Then when continuous function given, we could just substitute the c into the function, similar as the value of the function. How to evaluate it is the way how we evaluate the limit. But also, also some other properties, right? If we have the limit of function f and function g exist equal L and the k, then we could have scalar multiplying is b times L. The linear combination, sum or difference, that is the combination of their limit value. Product equal product, and of course quotient equal quotient. The case is when the k is not equal 0, right? Extra condition. And function to the nth power will be the limits to the nth power. Well, which means for most of the function, if the combination, like linear combination of products or quotient or power exponent, if original limit exists, then all of the other things exist. For especially something called composite functions, right? Composite by not only the summation of all the polynomials we have, but maybe the quotient we have, or the exponents we have, or the product we have for the function, even though like radicals, cubic radical, as long as certain value is inside the domain, is inside its domain, right? Then the expression is meaningful. Then we can evaluate the limit by just substitute the c value into the function. That's simply what these all things say. Right, so the limit analytically just defined by substituting. Right, if we cannot substitute, then if we simplify the expression, it can be substituted. Right, limit of 5 as x approaches to 2. So that here simply just 5. Well, when we do this limit as x approaches to 3 of x squared minus 5x, well, that is a simply nice function already, right? When we put 3 in there, we'll have no problem. We'll substitute. To get actually the limit to be actually as the function value, yeah, equal -6. The same way as we define. But the next limit this one, when x approaches 1, we get, if we substitute it, what we'll get will be 0 squared minus 5 times 0 plus 4 over 1 minus 1. I mean 1 squared minus 5 times 1. That we get is 1 minus 5 plus 4 is 0 over 0. It's the indeterminate form. So, which means we need to simplify a little bit before we do any substitution. Since the denominator is 1, since the denominator is 0, then the numerator is also 0, that we don't know what the value is actually is. It's indeterminate, it could be anything. So what we can do is, before we evaluate the limit, we keep it. But what we will do is try to simplify this expression. What we have is x minus 1 times x minus 4. That inside the expression x minus 1 can be cancelled out when x approaches to 1. Once again, it is not actually taking the value of 1. So the expression can be simplified when x is not 1. Right? This limit is take x only approach to 1. That doesn't mean x is 1. That just means x is close enough to 1. Right? It is very close that actually we cannot see the difference, but that is a difference. So x is not 1, therefore can be reduced out. We leave the expression x minus 4 there, then we can substitute 1 in. Before we substitute, we simplify the expression, so the limit notation should be still remains. And after we substitute the x value approaches to 1 into the function here, the limit expression could be thrown away. Right? So we get the limit. Right, so let's see about this. Similar. Now of the radical expression, to be clear that under the square root it could be 0 or larger. Right? So when we put negative 2 in there, that is square of negative 2 minus 4, which we get is 4 minus 4 is radical 0, where radical 0 is also 0. Right, so 0 inside radical is no problem at all, right? Especially square root is no problem. Right, something also here could be similar as what we have seen before. Right? When we put in equals 1, when we put in negative 1, we get 1 plus 1 minus 2, which is 0. The denominator is also 0. Right? So when we have the format of 0 over 0, which is indeterminate, that we can simplify the expression. Right, the factoring, I believe everyone know what to do. Right? The positive 1 and negative 2 multiply give us negative 2, sum to be negative 1, that's how we factor it. And when we have x plus 1 on the denominator, we are able to cancel it out to get x minus 2 only. We're able to cancel out when x is not equal to negative 1. It approaches to it means it's not equal to it. Now we are able to substitute negative 1 minus 2 is negative 3. Right, from last section, we have seen the expression x cubed minus 1 of x minus 1. We draw a table. We have seen that this value approaches to what? Approaches to 3. Right, so now let's see. X minus 1 is the factor. So even though we get both 0 over 0 on the top and on the bottom, we're able to find the limit by simplifying. or dividing it, right? If you factor it, it is a little harder. If you divide it, maybe also works. No matter we do dividing or factoring, we'll get x squared plus x plus 1. Now one substitute here, x squared plus x plus 1. That we get 1 plus 1 plus 1 is 3. It agrees with what we have found. Use our table. Right, so that is a special one, that we get a rational expression of polynomials on top and bottom. We're able to reduce, simplify it when we get 0 over 0. We're able to simplify it, which 0 over 0 means this approaching value is a root for both top and bottom, which means it should be a factor, x minus 1 and x minus 1, be a factor of the expression on top and bottom. Both of them should be the factor. Right? Then we simply cancelling out the factor will leave some expression doesn't have these factor in, and we're able to evaluate it. Right? The factor theorem in your pre-calculus, right? Which means if c is 0 of the polynomial, then the x minus c will be the factor of the polynomial. So which means both of the top and bottom, 1 is the 0 of them. That means x minus 1 will be both factors, or contains in both of the expression as a factor. But another type we actually have seen in the review is the radical expression. Right, this radical expression, when we simplify it, that is the format of 0 over 0. Of the format of 0 over 0. So when we simplify it, this one is not rational. This is rational expression, but that is a little special. Right? It is radical inside also, which the only way we can simplify the radical is to rationalize it. Right? To make the difference become a sum, then maybe easier to take the value. Right, as we do, we have multiply the conjugate pair, right? X plus 1 for the top and bottom. Then after multiplying the conjugate pair, everything will be able to do, probably. All we have on the top will be the square of x plus 1, of square of radical x plus 1 actually, minus the square of 1 over x times radical x plus 1 plus 1. That we get the numerator to be x plus 1 minus 1, that x is left over. So be careful that before we evaluate the limit, everything we have should be still copied down the limit notation. On this step, we see that x is contained in both top and bottom as a factor, so we reduce down. Numerator will have 1 left over. Well, we get this expression, 1 over radical x plus 1 plus 1. And when we substitute the 0 in, at this step we substitute, then we don't write the limit. Before we are just simplifying the expression, we should have limit notation all the way through. Right, then on the top we get 1, on the bottom we get square root of 1, which is 1 plus 1, that is 2. Or similarly, you can try this one, radical of x plus 5 minus 3 of x minus 4. From the beginning we can see it is 0 over 0, so we don't need to show it is 0 to 0. You could just multiply, conjugate pair. Which will give us an expression that x plus 5 minus the square of 3 and the bottom expression, which the top is x minus 4. And x minus 4 is a factor on both top and bottom that is able to be reduced. Right, to get 1 on the top. Therefore, the expression is simple enough that we can substitute the 4 in there. 1 over radical 4 plus 5 plus 3. Square root 9 is 6. Square root 9 is 3. 3 plus 3, that's 6. 1 over 6, that's the limit. Right, so that is the limit. Some special limits over there we are able to see. The first one is limit of x approaches to 0, sine x over x equals to 1. The second, limit x approaches to 0 of 1 minus cosine x over x equals to 0. The third one is when x approaches to 0, 1 plus x raised to the power 1 over x is a value e. I consider that we have indeterminate 0 over 0 form, we have indeterminate 0 over 0, and cosine 0 is 1, that is 0 over 0. We have the indeterminate form that x is very, very small enough that we get 1 plus x raised to the power of 1 over x is to the number e. Well, where e, I believe you have touched that before, right? The natural base, about 2.71828 something, right? So that three thing are special one. We'll touch more about what is how to evaluate the limit actually in our later chapter, maybe chapter 4 point something, right, in chapter 4. But these two, we're just using their results. Right, so we can try to use the numerically to see, to actually verify that the limit of sine x over x is 1 to verify that the limit as x approaches to 0 of 1 minus cosine x over x is 0. Right, so you can try it numerically. Right, so that is our section 2.2. Not 2.2, that is our section 2.3 actually. Right, evaluate the limit analytically, and next time we'll move on to something about continuity. Right, continuity. We actually have seen some cases that the picture. We have seen something like breaking point, something like even though they match. Right, something like this one is not breaking point, or something like in the middle is digging out, or defined somewhere, or maybe undefined somewhere. Continuous literally just meaning continuous, right? The graph is going on, move on, without any break. If the graph breaks, that's called discontinuity. And we'll see if we don't have the aid of graph, how we see a function is continuous, how we see if we have certain type of discontinuity of a function at the value c. Right, so that's what we will see in our section 2.4, our next section.